Okay, hello everybody. Welcome back to the third ever episode of say it with me, Ibrahim. Three, two, the
The
socks,
rest
the
is socks. You
so
didn't
the
say
rest is
one
socks.
again.
Yes,
Okay.
I thought you'd caught on by now.
Well,
Anyway,
clearly
today
not.
we have our first ever
No, second ever.
second special guest. I know what I'm talking about, Ibrahim.
Okay, okay.
It's our first ever second special guest. Please welcome to the stage, Sai.
Yo, thanks for having me on the show, guys. Great to be here.
It's not a
Okay.
show.
It's a podcast. It's a show just without any showing.
It's like a show and tell, but without the show part. It's just a tell.
We discussed this in the first episode as well.
I know.
Close
Um,
enough.
okay.
He clearly hasn't listened to it. Why is he here?
Moving
And this is
on.
the second episode.
Moving on.
Moving on.
Sai, what would you like to talk to us about today?
So, we're going to talk about infinity today, guys.
Okay.
One of
Yo.
the biggest paradoxes and most research to death topics in maths.
If you're not a maths nerd, you could, or like some sort of like a STEM nerd, you can clock off here. It's fine, guys. We'll forgive you.
Will we?
Yeah.
Okay, okay. Moving on.
All right, guys. What do you know about infinity?
It's very big.
I know that there's multiple types of infinity.
Because, so, the main thing when you think about infinity is people can't comprehend what that actually even means. Like, if you ask anybody, you could never truly get close enough to infinity. Like, and that's just
But
because we struggle to actually imagine what does infinity look like in day-to-day lives.
Yeah.
So, I mean, I think the best way to actually imagine it is probably when you look at fractals. Like, you can zoom in as many times as you want, but you create an infinitely repeating pattern, right?
Yeah.
So
um,
that's probably I'd say is just one of the coolest ways to see it.
Like it just goes on forever.
Yes, exactly. So one of the things though about infinity is like Louis mentioned that we can have infinities of different sizes. So that comes down to sort of the idea of what are the different types of infinity, which we define to be countable and uncountable infinities.
Okay.
So like a countable
and the,
infinity just means you could list every member in it, and even if it take you forever, you'd still well in theory you could still list every member without missing one in the middle.
mhm.
Yeah,
So
like
like
you could make an infinitely long list with every no. Yeah, okay.
And at some point in time, you'll get to any given member.
yeah, exactly. Like the natural numbers, for example, is a really good example. You could list all of them, or I suppose you could never really list all of them, but you wouldn't miss one out in the middle.
Yeah, you
There's
could
no
just do
natural
zero, one,
number
two, three, four, five, all the way
which
down.
you can give.
Hmm?
Yeah. So you're saying there's no natural number which I could say which wouldn't appear in our list.
Yes.
Yeah. Okay.
The difference though with an uncountable infinity, no matter what you do, you'll always miss an infinite number of numbers you could have said. So let's say I said 0.1, 0.2. There's an infinite number of numbers I could have picked from 0.1 to 0.2, but I didn't say. And that's the idea. Like every time, no matter how many decimal places you go, you'll always miss one out.
What are we talking? Wait, what group are we talking about?
The
Real numbers.
uncountable ones.
Oh yes, but what specific group of uncountable ones?
We're talking about the real numbers.
Just real numbers.
Yeah.
Because I believe there are a finitely infinite amount of rational numbers. Is that right?
Um,
Or
not
countable?
rational numbers, because with rational numbers, again, you can just keep on creating infinitely many. Because I could say 0.1 is rational, right? But then if I try to list all the rationals, all I have to do is increase by one decimal place each time.
Actually, I feel like we're gonna get fact checked on this, so
Wait,
I'm gonna
is
have to I'm gonna have to correct you there. So, in fact, because every rational number is created as have you seen like the Veritasium video with the proof of infinite buses or something.
Okay, I'll describe it now. I'll describe it now. So, rational numbers can be represented as a fraction a over b, where a and b
Yeah.
are themselves integers. So, you could sort of think about it like a grid, right? Where you have on top all the fractions with denominator 1, below that all the fractions with denominator 2, below that all the fractions with
I'll draw
denominator
the grid
3.
now for our audience to see.
Sorry?
I'll draw the grid now for our audience to see.
Yes, please. So you have that set which will contain all the rational numbers, and yeah, you may have duplicates. For example, 4/2 would be the same as 2/1, but you can ignore those.
And I'm holding it up to the mic. There.
Okay, they should be able to see it now.
Yeah.
Now, if you think about how can we list these off, you can't just go 1/1, 2/1, 3/1, 4/1, because eventually you're just going to keep on going on the top row, and you'll never reach the second row. So that's not going to work. But what you can do is sort of go off the diagonals, right? Where you have 1/1 in the top left, then you have 2/1 and 1/2, sort of one layer down from that. And then below that you have 1/3, 2/1, 1/2, and you have another row below that. And then you just keep going like that, where you do it off the diagonals. Then it does work. Then you can list them all.
Some numbers are double counted, but
Some
it's
numbers
fine
are double
because
counted.
You can just ignore the double counted numbers.
Yeah.
Yeah.
So this is one of those infinities where like, oh, it's bigger in size than natural numbers, but we can also then create even bigger infinities because we as human beings thought, why not make them even bigger? Because we can.
Okay.
And do you want to guess how you can make an even bigger infinity with your infinity you have right now?
The uncountable infinities are than the rational.
Add one.
We got those two, yeah. We got the uncountable infinity, we got the rational infinity, but how can
so
we make an even bigger one from it?
so we take it into like a discrete continuous dimensions.
So what we're going to do is to make these sets even bigger, we're going to count the number of power sets or subsets, okay? So
Okay.
a subset is like if you had like a list of numbers like 1, 2, 3, 4, and 5, a subset might be I just pick a couple of the elements and none of the elements.
Okay.
Now, the power set essentially tells you how many of every different combination is possible. And so let's take our uncountable infinity or the real numbers, right?
Yeah.
To make the power set, we take 2 and raise it to the infinity that represents the real numbers. And now we've created the essentially power set for the real numbers, which is way bigger because of exponentiation.
Okay. I guess yeah, that makes sense because each time you're either choosing to include or exclude one of the real. Yeah. Okay.
Yeah. So, but I think if I remember correctly, it's Cantor who was able to first prove that we got different size infinities, and I think everybody knows what his famous argument was.
Yes, but for the sake of our audience, would you like to tell us?
I will like to tell you, it's Cantor's diagonal argument. So
Oh,
Ibrahim's already
yes.
made some mention to it, but we're now going to slightly change the scenario so we make it uncountable rather than countable.
Okay.
So the way to think about Cantor's diagonal argument is it's essentially a proof by contradiction. We assume that all real numbers, we can list them somehow in a sequence. And so for the sake of argument, let's assume, I think, the only real numbers exist are at max 3 decimal places, right? And
Yeah.
so we list out all the numbers with 3 decimal places going
There are
downwards.
no other real numbers.
I mean, I would have thought
There
there
are
were
no
more,
other
but
real
okay.
numbers. No, there aren't. Ibrahim, what do you?
My mistake. My
I'm just
mistake.
keeping it simple because,
Yeah.
like, in
Okay.
reality, we'd basically say, oh, there's infinite number of decimals, and we're going to prove we can make another number somehow.
Yeah.
But what we do is we take, looking at the first number, we look at its first decimal number. So, for example, that might be 0.001, for example,
Oh, so
or and
all
on
of
and
them
on.
start with zero.
Hmm?
So all of them start with zero. Okay.
Like
And
real
then I would
numbers
say,
between 0
okay,
and 1.
Hold on. Let
and
me
we're
let
gonna
me
think.
show the audience. Okay, continue.
So what we're gonna say is now, taking that first decimal number, we're going to change it slightly, and the rule we use, we're just gonna add one to it.
Okay.
So 0 becomes 1. The second number, we're going to take the second decimal digit and add 1 to that as well. And we will keep going down to each number and we'll keep doing this. So all of these new digits we create, we'll put together to make a brand new number. And the neat thing is, it will have never shown up before because it's slightly different to every number that came before it.
Okay.
And that's how counter-diagonal argument works. It essentially means we can create and always create a new number that's slightly different to every other number, thus proving you can't count them all. And hence the name uncountable infinity.
So I saw once this really cool question on uncountable infinity. On uncountable infinity. Which asked, so if you take like a number line, and you've got all the numbers from 0 to 1, so obviously that's uncountable because we've
Yeah.
already stated that the irrational numbers are uncountable. And then, but uh, so are there more numbers from 0 to 1 than there are in a grid of uh of x and y coordinates, both of which are from 0 to 1? I'll let you think about this for a few seconds and then I'll tell you for the sake of time.
So what you're saying is like if you took like a grid
So
with
you've got
like
like, for
0 to
example,
1,
so are
with
there
like a
more
1 by
points
1
on that
grid,
grid or on the number line?
more
Or are
points in that
the
grid element.
or are they the
I'm
same?
tempted to say kind of no because like multiplying infinity doesn't change its size, but I'm interested in what
Okay.
the answer is.
So the answer actually is no, because let's say you've got a number, let's say you've got a point x equals like 0.462,
Okay. Okay.
and then y equal, this is completely random, arbitrary, y equals 0.918, and then they both repeat on forever. So, and then we're going to take a point on our number line. We'll call it Z because creativity. And so what we'll do is we'll take the first digit of so other than the 0 point, obviously, we'll take the first digit of x, so that's 4. The first digit of y, 9. The second digit of x, 6, 1, 2, 8. And we just keep continuing that for all of the digits.
Oh.
And now we've mapped
Oh,
each coordinate pair can only map to exactly one such number,
And each
which
number
means there
can only
must
map to
be,
one coordinate pair. Like it goes both ways.
yeah, yeah. So there must be the same amount, even though um, uh, the the line at y equals 0 contains all of the points on the number line, which is a really cool proof.
That is actually quite interesting.
that that sounds cool.
Yeah.
I think I have a puzzle of my own where, let's say you're in an infinite orchard, right? With a tree at every integer coordinate point. And you yourself are sat at the origin. And let's assume each tree is infinitely thin. So it feels like everywhere you look, there would be a tree somewhere down the line, right? Like if you go far enough, eventually you'll hit a tree.
Yeah.
But interestingly, our science has shown that there are an uncountably infinite number of real numbers. If you have a look at the gradients of where you could look, everywhere where you hit a tree, the gradient has to be rational, right? Because it has to go from the origin to some integer coordinate point. So,
Yeah.
because there's only countably many rational numbers and uncountably many irrational numbers, that means that almost everywhere you look, if you pick a random direction, you're 100% likely to not see a tree.
That's quite cool when you think about
That's assuming that you don't have an infinite field of vision.
it.
Yeah, assuming you only see what's directly in front of you. and the ocean goes on forever, and each tree is infinitely thin, you will never be able to see a tree.
And you're
And
picking
you're
completely randomly. And
And you're picking
for
absolutely randomly.
and
this is
you're also
it's
assuming
making a
that
lot
like
of
they're not gonna look.
assumptions. If you just had a couple big trees and the
Well, yeah, if you give the tree some thickness, then everywhere you look will be a tree, because you have some margin for error there.
yeah.
Same as if you give your vision
Wait,
some thickness as
wait. So,
well.
but if they're infinitely thin, how do you see the tree then?
Well, if you're looking directly at it, you can't tell there's a tree there. It's just that,
So it's
like,
like your vision is actually one dimension. Um and
Oh,
it's more
okay.
specifically the Y dimension. Um uh and you like Ibrahim have no depth perception.
okay,
Now,
Um so um I forgot where I was going with that.
okay. Moving
well,
on.
I would like now. So we just talked around a lot about comparing sizes of infinities, and so what I also want to kind of think about is like, where do we actually even use infinity? Like, do you guys have any guesses where do we use infinity in?
When we're talking about big things.
Um, is used in like electrical engineering.
Oh, of course it's
A
using
little,
electrical engineering.
a
Of
little bit,
course.
yeah.
Yeah.
The one I was going for was black holes and singularities.
Okay.
Oh,
So, see, when Einstein created his predictions, right, his equations are saying that when we're at the center of a black hole, there's apparently an infinite density. So now, I don't know about you, but do you
That's quite
guys think it's
dense.
possible for something to be infinitely dense? Like, what does that even mean?
if you've got like two particles inside of each other, is that infinite dense or is that just double the
I think
density?
that's just double the density. I think infinitely
Yes,
dense.
you'd need the entire universe in one particle.
Well, no, that'll still be finitely dense because the universe is finitely
But you
massive.
need, fine, you need the entire
But if
multiverse.
we, Ibrahim, if we're saying that we have got an infinitely expanding universe, what does that mean then?
That means that we've got
Like
the
it,
like
the universe
furthest
expands
planet.
infinitely in time, or it's infinitely large.
We'll go for it expanding infinitely.
I don't think it's like mass is expanding though.
That's true.
Well, okay, to me, infinite density feels like you have some mass in exactly zero space.
Yeah.
Or
Yeah.
It's kind
infinite mass
of
in
kind of weird
exactly
things.
some
I
space.
feel like what we have is a bit.
So you were
I just
saying?
think maybe I think probably is like we can't imagine what that looks like, and I don't think anyone's gonna be able to make it to the center of a black hole and back out without becoming permanently deformed. So we'll
Yeah,
never
you
know.
can't leave a black hole once you go in.
Yeah,
What if
unless
you've got
someone.
like a chain and like just when you're ready to come out the black hole, or when the scientists are ready to bring you back out the black hole, they just like pull up the chain and then you go back onto the ship.
So your idea is to just tie a chain around their waist, throw them in, and yoink them out once they're done.
Or like a bungee cord. Yeah. It sounds dumb when you say a chain because they'll just get like torn in half or something.
I
But then
feel
you
like.
attach it.
A bungee cord would also get torn in half.
But yeah, but the person wouldn't get torn in half.
Yeah, I feel like the person would die before they got that far, and
Well,
unless it's like
interestingly,
Interstellar,
Okay,
then
what
we don't
about a
know.
light inextensible rod? Surely that'd be fine.
Hmm.
I mean, the rod has no mass, but at any force that the rod could impart on you wouldn't be enough to get you to leave the black hole.
But it's
Yeah.
inextensible.
No, but like, how would you get out again? Like, that's the problem. Like saying we could send you in, sure, but who's pulling you back out?
Okay, so you
Okay,
attach a
here's
person to either side of this inextensible rod, and the rod has a diameter, has a length larger than the diameter of of the black hole, and so when it sucks you in, you actually like come out the other side, and then you're being kept like afloat by the fact that there's a person on the other side.
well, because of the way space warps around a black hole, the diameter of a black hole, as measured from the inside, is infinite.
Yeah. Well,
No fun.
Okay, let's have a quick crash course on black holes, guys. So, you're going into a black hole, you're just about to cross the event horizon. Right? Or actually, no, you are crossing the event horizon. The event horizon is the point at which once light goes in, it can't escape. But the reason why that happens is because at the event horizon and beyond that, space is warped so much that space and time sort of swap, right? In that the singularity is not the center of the black hole for you anymore. It's now a point in your future.
it's like time dilates around you rather than
Yeah.
like normal kind of thing.
What were we
Interestingly,
talking about infinity?
well, I
I
guess
mean,
time dilation happens so much on the surface of the black hole that if you were on the surface of the black hole, by the time 1 second had passed for you, an infinite amount of time would have passed in the rest of the universe. Like you would see
But
the
isn't the black
entirety
hole
of the
blow
future
up
of the
by then?
universe. Sorry?
Doesn't the black hole blow up by then?
Ooh, that's a good question. I think if assuming the black hole is infinite, that's what you would see. But obviously, because you're still
um,
traveling into the black hole, then it would be the time you spend on the event horizon would be instantaneous.
yeah,
Okay.
that's quite crazy to think about. Like
Yeah.
you could spend a mere second on the event horizon and an infinite number of time could have passed them. So would that be, but like say you managed to get that far and survive all that? Does that mean Earth would have been blown to bits by the time you were done?
Oh, absolutely.
Well, so what the black hole you're in? I'm really confused. But that's like what happens at the heat death of the universe. The heat dies. The
Yeah,
black holes like explode like a fireworks show.
I think so. Yeah.
Yeah, because of Hawking radiation.
So back to
I guess this
infinity.
is. I guess your experience would be different from the black hole's experience, just because you're both in different. Because the black hole's
Yeah.
experience is based on the environment around it, but your experience is influenced by the black hole.
Yeah, I think that sums up pretty well.
Okay.
Okay, like Louis said, back to infinity.
Yeah.
Yeah, I did say that,
So
didn't I?
no, that's what I think is quite cool about infinity is that ordinary operations seem to fail once we start applying infinity. Like if you added one to the natural numbers, the cardinality doesn't change because what we say is when we compare the size of infinities, we compare them by trying to establish something called a bijection between them.
Okay.
Um, Bijections just mean that you prove two sets are equal if you can map each member to a unique member in the other group and vice versa.
Oh,
Oh, like Louis
there's
did with the line and the square.
I mean,
Yeah,
I didn't really map two separate points. I love this proof because my favorite part is like the square numbers. There are as many like square numbers as there are whole numbers because you can map each whole number to a square number even if there are some whole numbers which aren't square numbers.
Yeah.
yeah. And honestly, that's the interesting thing is like, to what extent does infinity actually make sense to us, and how much we still have to figure out? Because I think one of the key mysteries we still have left that we have no idea about is the idea we have the countable infinity, right? Of we got our natural numbers, we've got the uncountable infinity of the real numbers, but we know that infinity is bigger than those two. But what we don't know is there an infinity between the two of them,
Like
and
higher
that's
than
called the
countable but lower than uncountable.
yeah, and that's called the continuum hypothesis.
Okay.
So it's just asking that question, can we find the infinity between countable infinities and the cardinality of real numbers? And so Cantor thought that no intermediate should exist, but Gödel and Cohen proved that we can't answer this question with what we know.
Okay.
And see, here's the problem.
How would you go about answering that? Because you can either list it or you can't. And if you can list it, then by definition it's countable. And if not, then
Yeah,
by definition it's uncountable. So how would you go about like finding one in the middle?
that's the problem. We don't have the maths yet to do it.
Okay.
So the problem is, we also have the other problem of, so I'll call it CH for sure, but regardless of whether CH is true or false, they're both, it turns out, equally valid. Like what axiom we choose doesn't actually matter, it turns out. So while we don't know the answer to it, it doesn't cause us a problem with other calculations.
Okay.
So
Okay.
right
So
now,
whether or not it's true or false, it doesn't actually affect other areas of maths.
yeah, if we
Okay.
pick either true or false, they technically are both correct. And it just depends how do we construct the math, really.
Okay.
So really, infinity is basically so wild to the point we as mathematicians can't even contain it.
Yeah, it's really big.
Yeah, I know it surprised me when I learned how big it really was.
It's it's almost like they should make a word for how big it is.
I think
Um,
infinity is a pretty good word. What do you think, Louis?
I
I was
think it's a
thinking
pretty good word.
infinitely because like it's like an adverb.
Oh, like an adjective, yeah.
No, an adverb.
No? Okay. Well, with
Um,
that, we are about 5 minutes out from half hour. So, are there
so
any
so
final
we
things
need to
Si wants to
take this
say?
time to tell you about our sponsor.
Please sponsor
Um,
us.
no, I've already made that joke twice, Ibrahim. It doesn't work a third time. Like if
Okay,
you
but
make
I
that joke,
haven't.
it's
Okay.
it, fine. You can make the joke. You can make the joke. I'll judge you.
So,
Okay.
time for our sponsor, guys. Please sponsor us because we low-key want money.
Uh,
Um, yeah.
no,
The judging
it,
sounds are insane.
I'm judging because it's like the third time and you're just bad at it.
Okay, okay. Well, Si,
It's nothing personal.
are there any
Um,
closing remarks you
Well,
want to say, Si?
well, honestly, if I was to end off, I'd just say infinity is one of the few topics in maths where you've got to realize the traditional rules no longer work. You've got to like quite literally redefine how we think about it. But at the same time, it is something really cool to see in real life. I genuinely will still say fractals are the best way to see infinity. Just they got some of the best patterns, and like it's an infinitely repeating pattern no matter how much you zoom in. Like you can't argue with that.
that is
Very
cool.
nice. So, thank you
I
all for
think,
listening, guys. Louis, are you gonna
Um,
say thanks, or are you still
no,
upset about
no,
my joke?
I'm not upset about your joke. I was just thinking of fractals. I went to this lecture the other day where it said that fractals had like partial dimension, um, which is cool.
That's very cool.
Um, but but yeah, that's the story for another time.
Yeah,
Thank you everybody for not watching.
for listening.
Thanks to our one listener. And we'll see you personally next time. We won't see you. You'll hear us.
Yeah,
Okay.
bye.